Okay, so this is experiment number 2. This is the steam distillation. We are going to steam distill trans-Cinnamaldehyde from cinnamon bark. Just a brief background. The pre-lab lecture video explains in greater detail, but let's remind ourselves that distillation is the technique whereby a liquid is converted into a vapor and then back condensing to its liquid phase. So this is vaporization and condensation. So the distillation is very prevalent as a practical technique for organic chemists. And then we divide them into 3 major types: steam distillation, simple, and fractional distillation. We are going to start with steam distillation. The next experiment will talk about the simple and fractional distillation processes. And these distillations we perform at or below atmospheric pressure. Today we're going to do it at atmospheric pressure, but if it were performed at reduced pressure, that is to say if we used a vacuum, we wouldn't have to heat the liquid in the distillation pot as high, but here we don't care too much about that. Steam distillation is a very old process. In fact, it dates back to ancient Egypt, where it's been written that they were making perfumes via this very same method. And basically, if you've got a natural product like a flower, or in this case, a cinnamon stick, if you could smell something aromatic, it's likely that you might be able to steam distill it and isolate that essential oil, or the main component of the essential oil, and of course then later determine its structure, etc. So here we've got some cinnamon sticks. It's sold out of Oceanside, New York, but it doesn't tell us where it was shipped from. Most likely either from India or China. They are the biggest producers of cinnamon. And so if we just take a look, this is actual cinnamon bark. Usually when we're in the kitchen we see it as a powder, but here's some bark of cinnamon. It smells very nice the moment you open it. Of course we know that cinnamon is used for a variety of food stuffs, right? Tea, gingerbread, even cereal, what have you. Cinnamon is considered a natural product, and where it is isolated from is a tree, obviously, because we've got it as bark, and the compound, the organic compound that we're trying to isolate, is called trans-Cinnamaldehyde. And this is the principal component of cinnamon that gives it its smell. So, in fact, we've got a bottle of trans-Cinnamaldehyde sold from Aldrich, a very famous chemical company, which is pure trans-Cinnamaldehyde. And you see that it's a free-flowing liquid, and the minute that you open the cap of the bottle, it smells just like cinnamon. So trans-Cinnamaldehyde has been identified as the smell of cinnamon, but since we're dealing with the natural product itself, also what will steam distill over as the essential oil are other components. So for example, eugenol, which is this structure here, is also part of the essential oil of the cinnamon. Just as a side note, this is from the Lauraceae family, and specifically the most commercially grown cinnamon is Cinnamomum virum. So that's most likely these cinnamon sticks. So we need to crush up the cinnamon. So I've already started, and I've gotten a nice glass mortar and pestle. And so I've ground up some cinnamon, and we need about 1 gram of cinnamon bark. And so what we're going to do is we're going to take our notebook, walk over to the balance, and try and weigh out around 1 gram. Since we're using an analytical balance, we'll know 4 significant digits. All right, so we're back at the balance. Close all the doors, tare it, and then I've got to get a scoop. So this is a scoopula. I'm going to use this to transfer some of the cinnamon bark from the mortar and try and get around 1 gram. So here's 0.9, getting close. Okay, wow, pretty good. So according to that, it's about 1 gram. Is it spot on? Probably not, but 1.003, let it just settle for a second. And of course, we want to, where did that pen go? Did it fall? There it is. We want to write down in our notebook how much cinnamon bark we actually weigh out. So we started with 1.006 grams of cinnamon bark. And the cinnamon bark, from it, we are going to steam distill out trans-Cinnamaldehyde. If this were to be performed on a much larger scale, we would see that there would actually be 2 layers that formed in the distillation process. There would be a bottom layer which would be aqueous, and then a less dense layer on top, which would be the essential oil trans-Cinnamaldehyde, which is less dense than water. Since we're doing this on a small scale, and this is not a natural product isolation type apparatus, then we have to be vigilant about how we're going to go about collecting our distillate. Okay, so we've got 1.006 grams. I'm going to take my cinnamon bark on the weighing paper, carefully travel over to my lab bench. What we're going to do is that we're going to transfer the cinnamon bark to a 10 milliliter round bottomed flask. So this is a 10 milliliter round bottom flask. This is in our microscale kit. Obviously it's got a round bottom. It can't sit up straight, so we've used a 50 milliliter beaker to just support it. In terms of transferring solid to a flask, rather than bending the filter paper, what's nice is to take the 2 front edges and make a type of cone like this, where you can then make your own funnel and transfer the solid this way. So, and then you can use a little, you could scrape it down with the scoopula, but what I've done is I've transferred now the cinnamon bark to the 10 milliliter round bottom flask. And what we are going to do is that we're going to add 4 milliliters of distilled water, and so I'm going to use my graduated cylinder, adding 4 milliliters of deionized water, and we're going to add this to the round bottom flask. All right, and so obviously this is the water that we're going to use to steam distill out the essential oil, the trans-Cinnamaldehyde. All right, so the rest of the setup looks like this. So what we've done ahead of time is that we've got our porcelain crucible with sand, and we've already started the heat setting at around 5 to 6. So this is our hot sand bath. So this is what we're going to use to boil the water and affect our steam distillation. The rest of the setup we can see is already connected to the ring stand, and what I'll do is I'll explain what's going on with these individual pieces. And so the one that I'm going to show you now, this one here is called an air condenser. It's called an air condenser because it's being cooled by the air in the laboratory, and any steam that might eventually travel up the vapor, the steam itself will condense and then come back down. When we are connecting the two things, we see that there's a Teflon O-ring here, this black O-ring. Actually, it's a type of rubber, it's not Teflon. And then this red screw cap. This will help seal what we're connecting it to. The joint size here is 1410, and we are going to, and this is the male end, and we are going to attach it to the top of my distillation system. This is called a Hickman-Hinkle still. It's a distillation still, and if you look at it up close, what you can see is that I've got a side arm here. This is where I'm going to retrieve my milky distillate from with a pasteur pipette once we start the process. But then also what you can see is the glass is sort of looks like a donut on the inside here, where the walls here will collect the filtrate. As the steam travels upward, it'll condense on this glass, the cooled glass, fall back down, and pool here. And that's what we're going to collect as our distillate. Since we're going to be removing liquid, we're going to want to be sure that we maintain the volume, approximately 4 milliliters of distilled water in our round-bottomed flask. So we're going to connect this as well, clamp it right at the top of the Hickman-Hinkle still head, and I'm going to center my round bottom flask, and we want to have it 90 degrees to the lab bench. And so now at this point we're just going to have to wait for it to boil. If you want it to be good about it, you can use a scrupula or your micro spatula to make sure that the sand is touching all the parts of the round bottom flask. You can bury it a little bit more. I don't like to, because I want to be able to see how much volume is down there, because I don't want to actually burn the cinnamon bark. But you can already see that it's starting to steam somewhat, and steam and then collect on the edges here, because we had this sand bath going pretty earlier, and it's probably going to start boiling pretty quickly. In these cases, since we've got cinnamon bark there, we did not add a stir bar. In the future experiments, we'll learn about the Teflon-coated magnetic stir bars. But in this particular experiment, we're going to just let the cinnamon bark prevent what's known as bumping of the boiling liquid. And bumping, what I mean by that is that you can superheat a liquid, and if there's nothing that's stirring around, it could superheat and then bubble all the way up and out of your distillation setup. The technical term are sites of nucleation, and so that could be, for instance, a crack in the glass, the stir bar itself, but in this instance it's going to be the cinnamon bark acting as that. And so if we get a nice closer in picture here, we see that we've got water condensing. Right, so it's definitely starting to heat up, it's steaming, And essentially what we're going to wait for is that for this to boil and heat this part of the glassware that's going to travel upward to the Hickman-Hinkle stillhead. Because what's going to happen is that as the steam is traveling upwards, it's going to condense on the cooled glass and then come back down. Right, this is part of the distillation process. We're going from liquid to vapor and then from vapor to liquid. The steam is going to heat this part of the glass so that the steam won't condense on it anymore, because it's going to be the same temperature as the steam itself. So it has to heat the glassware as it's traveling upward, and then finally reach an area where it's cool enough, for example, all the way up here on the air condenser, where it will condense, come back down, and then it's going to pool here where we're going to collect the distillate. If we need to, we can use some aluminum foil to sort of tent the distillation setup so that we can insulate the glassware and be sure that the distillation is going at a nice steady pace. What's nice to do is to have, since we want to maintain the volume of water down there, we've got the 50 milliliter flask that we used to nestle the round bottom flask in. What we can do is we can actually have some distilled water in there, and in order to maintain the volume. So let's just put a random 10 milliliters in there, or a little bit more. It doesn't have to be exact. And so then this way, the water is heating, and so when we're going to transfer it back down into the distillation pot, we don't have to wait so long for it to heat up again. So we're going to wait for that, and then we'll come back and demonstrate how we're going to collect the distillate. But what we're going to use is this 9-inch pasture pipette and the rubber pasture pipette bowl. So they connect like this. You got to make sure you've got a nice seal, and otherwise you won't be able to draw up liquid. So for example, now if I were to put 6 milliliters of water in there, you can see that I can nicely draw up some of the liquid, right? And so that's how we use the pasture pipette, of course named after Louis Pasteur. So we'll see that this is how we're going to use this to draw out the liquid here, the distillate, and collect it in what's called a culture tube. So this is a culture tube. It's essentially a test tube, but it's got an area here where you can screw on a cap. And we're going to want to obtain about 6 milliliters of distillate. So how do we know what 6 milliliters looks like? Well, hey, I just put 6 milliliters of water in this. Let's just go ahead and measure what that would look like. So we want to get to about there. In fact, we can even use a Sharpie if we wanted to mark the level at which we're hoping to collect distillate. So this is 6 milliliters. And don't worry about the glass. If we wanted to, the Sharpie will come off. So just below the little white etched portion where you can draw on as well. So this is the amount of distillate that we're hoping to collect. All right, so this is going to be a video on how to tear a culture tube. And so what I've already done is I've written tear weight on it with graphite and a math analytical balance. Who knows what the previous person left on the balance? So I'm going to use a piece of weighing paper to protect my culture tube, so to speak. I'm going to tear the balance itself now, and I can even leave it like this if you don't want to have it edge on and roll off the plate of the balance. And it's reading at 11.620 grams. That is now the tear weight of my culture tube. There's nothing in it, so it's the tear weight. So I'm going to write that on the side of the culture tube, but I'm immediately going to also now write it down in my notebook. So this is the tare weight of the culture tube. And it's 11.622 grams. That way I'll never forget it. And then I can also, if I want to conveniently have it later, write it down on here as well. 11.622 grams. All right, and that's how you tare a culture tube. Okay, so we've reached steam distillation now. You can see in the very bottom part our distillation pot, the 10 milliliter round bottom flask. It's clearly boiling. The water is taking on some of the color of the cinnamon bark, and we can see that the vapors have been climbing upward. They've reached the Hickman-Hickel, distillation head, and we can see that the vapors are condensing. This is the steam distillate, so we're waiting for this to condense and then pool in this area here. But this is what we want to see. This means that our distillation is going well, and now all we have to do is be patient. If you are impatient, you might use some foil in order to insulate this, but there's really no need for that. So we're just going to wait, and then what I've got here is my test tube rack, and here's my culture tube where I had the 6 milliliters marked. And what I'm going to do is I'm going to take out the distillate and transfer it into there. And every time I take a little bit out, I'm going to use a separate pasture pipette to add more water down into the distillation pot, okay? And I'm going to want to aim it down the center so that it, of course, doesn't pool with the distillate itself, because then you're just collecting too much pure water again. But we'll emphasize that again shortly. So we see that it's collecting, we just have to wait a little bit. All right, so this process actually is taking a good amount of time. So we have decided to use aluminum foil to tent it. So this is just a fancy little holder of a roll of aluminum foil. I don't have to take off too much. Should be enough. And what I'm going to do is I'm going to just very loosely tent this area. And so what this is going to do is it's going to insulate the boiling pot, the distillation pot, so that it'll hopefully distill faster. And it's loosely held here, and what it's doing is it's maintaining a pocket of air in there, and preventing the very cold, it's cold in here, the very cold laboratory air from hitting the neck of the still head, and just condensing back down into the distillation pot. So it itself, without the tent, is almost acting like an air condenser. And so now hopefully what we're going to see is that actually we can see it quite clearly, is that we've got more steam vapors that are traveling upwards now due to the fact that we've tented our unit with foil, and hopefully now we'll be able to see that more distillate, and we can collect at a faster rate. All right, so we've got a good amount in the well of the still head that we can begin to collect our distillate. So I'm going to be sure to use the same pasture pipette every time I draw out the distillate. And so here once again is my culture tube marked to the 6 milliliter. And I'm going to unscrew this little cap, and I want to very quickly dive down with my pasture pipette and draw up the milky distillate. So if you look at my pasture pipette now, in there, that's the milky distillate that we're trying to collect. right? And it's milky because the cinnamaldehyde is not soluble in water. And at the same time, with my left hand, I've put the screw back on because we want to be sure that nothing is escaping. We don't want the steam to leave our distillation head and then us not be able to capture it. All right, so we're doing a great job. We can also see now at this point that the steam has reached the air condenser. It's gone all the way up here, and to both of us, it's smelling very cinnamony in here. But remember that I said we wanted to maintain the volume down here below because we don't want to burn the bark or just heat it to dryness. So I have some water on the side, and I'm going to dive down very carefully, and I'm adding more water to the distillation head. Excuse me, to the distillation pot. So my pasture pipette is bypassing this, so I'm making sure that I'm not adding water to the area in which we're actually hoping to collect the distillate. And I'm going to reserve this pasture pipette in order to do that, and this one in order to collect distillate. But right now, this rate at which it's going is pretty good. We don't want to have a volume greater than what we had originally observed, because once again, that bumping effect that I had mentioned, it could superheat and then actually literally bump upward, and then some of the bark could reach this area instead, and it doesn't work out in your favor, obviously, because you want milky distillate to look like this. You don't want to have brown bark carry over, and that's a very common issue when you begin to use the foil and then you leave it on there, or if you add too much water. And so this is good. I think I'm going to leave the foil off for a minute, and if we get in really close, try and focus. All right, this is the area where the distillate is collecting. So right in here. So we're going to let that build up every time that we unscrew the cap here, and wait for it. All right, so you can see that coming down, that just dropped into there. That's the distillate, and it's condensing all the way up to this air condenser. It hasn't left just yet. We're relying on the very cold air of the lab for this the steam to condense, meaning going from vapor all the way up here now, condensing back into the liquid state and falling down and collecting in this pool right there. Okay, and there's our distillation pot, it's called, and that's the 10 milliliter round bottom flask with the bark in it. So this is like a fantastic operation that we've got going on right now, and so there looks to be enough in there to continue to draw out the distillate. So I'm unscrewing this cap here. Oh, maybe there's not enough. Why can't I grab any of it? There we go. Well, the issue is the angle at which the pasteur pipette was in there. I definitely don't want to break it. And we're still going. All right, so it's pretty much just a waiting game for this steam distillation. If you were to do this on a large industrial scale, you would have a fancier setup, obviously, and it would be is called lighter than water extraction, and you would use a special device. It's a piece of glassware in order to continuously extract out or distill out the organic components, and it's such a specific type of glass that it's a continuous distillation. So in that sense, when you're doing it on a large scale, if you're a natural products chemist and you're focusing on isolation, you don't have to worry about continuing to add water. You can just sort of set it and forget it and come back. But here we've got to monitor what we're doing. When you're doing it on that large of a scale, obviously you can still have some milky distillate, but it's so large that, once again, you have two phases. You'll see two layers. And we'll talk more about that when we perform the extraction process part of this experiment. Good. All right, so every time you do an experiment, you learn something new. I was growing impatient, waiting for the distillation to speed up. But what I've decided is that I put a little bit of chipped ice in a paper towel, and I'm just touching the edge of the still here, so that the distillate, the steam, the vapor, will condense faster and hopefully pool under here at a faster rate as a result, because it's now got cooler glassware up here to then condense on. Another thing that I've noticed that I had mentioned we are trying to avoid is that if you look down here really closely, you can see that the boiling is fine, but we're concerned about it bumping and then traveling upwards due to the fact that it's sort of soapy at this point. You can look up saponin in natural products that we're trying to avoid here. And so I've noticed that it happens when I unscrew this. At the most, it occurs when I unscrew this, and then there's some change in pressure in there. So what I've decided to do now is that every time I take distillate out, I'm also going to raise the whole thing to avoid that, because I really do not want any bark or brown material to collect in my still head. All right, and still, we can see it's still pretty milky, so this is still going great. Once it begins to be just clear, if it's just water, then we know that we've steam distilled out as much as we possibly can. But since it's still milky, we're going to continue with the steam distillation. So now I'm going to put it back and hope that it won't bump, that issue. And also this ice in the paper towel trick seems to be working in my favor. So that's an adjustment to the experiment to take note of. So we're also interested in knowing the temperature of the distillate itself. So the steam, the vapor. We know water boils at 100 degrees Celsius, but when you've got other components in there, it depresses the boiling point. So we should see that the steam shouldn't be, it should be less than 100 degrees. So I've got my digital thermometer, and what I've done is I've pierced it through a microscale septum, and it's just made out of basic rubber, just pierced it, and so that way it can hang out here and not fall all the way down. So right now it's 22.9 degrees in here, and I'm going to dive down, and I'm going to, once again, I'm just going to try to get in that area of the still head to record the temperature at which the vapors are condensing. And the thermometer right now reads 58, and it's still climbing. It's right in the center there. and I'm holding the bottom part of it so that the probe isn't touching the side of the wall. I want to get it centered so that it's actually in the arena of where the vapors are traveling upward. So it seems like it's hovering around what we've been noticing mostly, about 62. Oh, it's going up. All right, never mind. I'm also pushing down on the whole thing, steadying my hand, so the round bottom flask is facing the heat. Still climbing. And so if you look at the still head, look at where I've got the probe. You might be able to see through it. Down in here, you can actually see some of the vapors condensing on the probe itself. So that really is the true temperature of the distillate, and it's now pretty consistent. It's around 75 degrees. So we're gonna, and of course, once I say it, it increases. No, it's hovering around 75 to 76 degrees. So that's what we're gonna say. 75 to 76 is the temperature of the distillate as it's collecting. Okay, so now begins the extraction process. So we've collected approximately 6 milliliters of distillate, and so what we want to do now is use an organic solvent to extract out the lipophilic, that is to say hydrophobic trans-Cinnamaldehyde. And what we're going to use is methylene chloride, CH2Cl2, also known as dichloromethane. It's a very common solvent. And its density is 1.33 milligrams per microliter, so it's heavier than water. So we're going to do 3 extractions with 2 ml of methylene chloride and combine the organic layers. So you'll note that once I add this methylene chloride, the layers, 2 layers form, and you see that the methylene chloride is hitting the basement level, so to speak. And once again, that's because it is more dense than water. And so now we've got 2 phases. We've got the top aqueous phase and the lower organic phase. Also, we can say this is the top aqueous layer and the lower organic layer. And so we want to gently shake this in order for the 2 to mix again and try and extract out as much cinnamaldehyde as it can into the first organic wash, we can call it, of the extraction procedure. So I need a little screw cap. Alright, so the culture tube has the thread for a screw cap like this. I don't want to shake it too much because it tends to leak. It's not sort of watertight. So I'm just going to shake it like this, and the methylene chloride is going to meet the aqueous layer, and the more lipophilic trans-Cinnamaldehyde is going to be more soluble in the organic layer, the bottom organic layer. All right, And so now what we're going to do is we're going to let this sit so that the two layers separate out. We can see that the top aqueous layer has become a little cloudy actually, and the lower methylene chloride layer should have taken out a really good amount of our organic product or organic material that we're trying to isolate. And so I'm going to use a new pipette, and I'm going to take out the first 2 milliliters of methylene chloride for this extraction procedure. And so I've got my culture tube where I'm going to combine 3 times 2 milliliters of methylene chloride, because I'm going to do that whole extraction process 3 times total. So I like to have them side by side, and my pipette is diving down, and I'm drawing up the organic layer, and I'm transferring it to this other culture tube. And I'm trying to be as careful as possible to avoid any of the water that I can see. All right, so that's the first extraction. So on the right side is the methylene chloride. That's our organic layer that I just separated, and on the left side is the aqueous phase, our original distillate. So I set that one aside. Once again, I'm going to use another 2 milliliters of methylene chloride, using a disposable graduated pipette. Add the methylene chloride. Once again, it sinks to the bottom. I'm going to gently shake after I screw on the cap. And this is now the second extraction, and organic chemists call them a wash, is another way to say it. And I wait for the two phases to separate. Sometimes you can see, if you ended up shaking it too hard, right in between the lower and upper phase is the interphase. And sometimes you can create an emulsion, and that is very difficult to deal with, because then it's hard to differentiate between the organic and aqueous layer. And if you make an emulsion, then it won't separate at all. And there are tricks to solving that issue, but I'm not going to create it for you. So once again, now I'm getting the second organic layer, and I'm combining it with the first, and trying to be careful to avoid any water. All right, and that's the second extraction. And now for the final third extraction. The last 2 milliliters to do this. And then in total, we'll have a combined 6 milliliter organic layer. Third, and so this is the final extraction, and I've got my combined organic layers. So I was very careful not to get, or trying to avoid any water from transferring over. However, there's still going to be water that we cannot see. So if we were to see water, we would see it on top, and typically it tends to stick to the glass. So I'm not sure if the camera can capture this well enough, but there are little water droplets floating on the surface of the methylene chloride. So that's some water that I can see, and there's also about 3% that I cannot see. in fact, if I shake it, you can sort of see them moving around and then flying upward. So, but that was a pretty good extraction. A lot of times you'll end up seeing there's water stuck to the sides of the glass because someone didn't do such a great job avoiding the water. But anyhow, to get rid of the water, we are going to use a drying agent. And the drying agent that we are going to use is called sodium sulfate. This is a salt. It comes granular anhydrous, meaning it's without water. It also comes as a powder, but the granular stuff is the better one to use. And what it's going to do is that for every one molecule of sodium sulfate, it's going to grab about 9 molecules of water out of my combined organic layers. So this is how we're going to, quote, dry the organic layer. And this is going to get rid of any water that we don't want around, because of course we don't want that to be part of our final weight. So I'm using a scoopula to just add some. And so the first round, just that little bit, do you see how it's sticking to the sides of the glass? And the sodium sulfate has sort of increased in size. So that's just an indicator that it's taken on some water. And so we usually say that you want to look for a snow globe effect, which means that there's free-flowing sodium sulfate that looks like its original form, so that you can say, oh yes, this is dry enough. Put the cap on just to be safe. And so it's sort of turned into a chunky rock at the bottom there. But I have some that's flowing freely, so this is good enough. I also want to point out, so this is our organic layer, remember. If you had accidentally forgotten which one it was, this is the aqueous layer. Once you put sodium sulfate in it, it of course dissolves in water because it's a salt. All right, so now the last line of defense is to use a column of sodium sulfate. So this is a 5 3/4 inch pasture pipette. There's a little bit of cotton here, and then above it is a column of sodium sulfate. So this is going to do two things. It's going to dry the organic layer even further, and it's also going to act as a filter. And so I'm going to now recall the fact that I tared my culture tube earlier, and this is where we're going to put our dry organic layer into. For this process, I want to use a new pasture pipette because all of the other ones have seen water at some point. Okay, so here is my dried organic layer, and I'm going to use a brand new pasture pipette that hasn't seen any water, and I'm going to draw up my dried organic layer, and I'm going to drop it right into my column of sodium sulfate that was in my smaller pasture pipette. And it's going to filter through via gravity. If I accidentally draw up any of the solid through this pipette, as I had mentioned, it'll get filtered also. So this column is drying the organic layer even more, and it's going to filter any sodium sulfate that I might accidentally draw up. So you can see it's a pretty decent rate. If it were a slower rate, that would indicate that your organic layer was still really wet, and the sodium sulfate took on so much water that it acted more like a stopper than anything else. It could choke the filtration if you had too much water. All right, now here's the remaining. And then you can see that I've got the remaining sodium sulfate left, and we're not really getting much left, right? It's like at the bottom of your soda when you're being rude and trying to slurp it up. If you were being very efficient in terms of quantitative transfer, you could use a little bit more methylene chloride to rinse everything and then try and get everything over. But we're going to do it this way. Set that aside. And now what I've got is my dried organic layer in my culture tube with the tare weight. And once we evaporate off the methylene chloride, we can get the final weight of our aldehyde, and we can then calculate how much cinnamaldehyde we isolated from that original 1.006 grams of cinnamon bark. Typically, it's around 3%, so we'll see if we did a good job or not. All right, now since we've evaporated off the methylene chloride, we have the amount of trans-Cinnamaldehyde that we isolated, and we know the tare weight. So now we're going to weigh the culture tube with the trans-Cinnamaldehyde in it, and subtract the tare weight from that. And so this is 11.678. So this is 0.056 grams. So we've got about 56 milligrams of trans-Cinnamaldehyde that we isolated. So in our notebook we can say around 56 milligrams isolated. And then for the percent isolation, we're going to take that and divide by the original weight of the bark, which was 1.006 grams, multiplied by 100, and it's approximately 5% isolated. So 56 milligrams is about 5% isolated, which is pretty decent and rather typical for each year. So it's not as fun because you can't smell how nice it is, but we just isolated a natural product from cinnamon bark via steam distillation.